Hey, welcome back. Today we are going to learn about parametrized curves. I think the best way to think about parametrized curves is that they are the most convenient way to describe one-dimensional objects in three-dimensional space. So today we're going to talk about what they are, what they mean, how to visualize them, and then we'll talk a little bit about what we can do using calculus and parametrized curves. Let's get into it. So it turns out that you actually already know about a type of parametrized curve because you know how to parametrize lines using vectors. So let's talk about that very briefly, partially as a review, but also just to lead into the definition of a parametrized curve. For example, let's say we wanted to describe the line that passes through the point 1, 2, 3 and is parallel to the vector 4, 5, 6. So just so that we have a picture, let's say that here's the point 1, 2, 3, and the vector 4, 5, 6 points this way. Then we want the line that goes through this point and is parallel to this arrow. So maybe it would look like this. Now, we already know from a couple lessons ago that we can describe the points on this line like this. They are all of the form the point 1, 2, 3 plus t times the vector 4, 5, 6. In other words, we think about it like we can get to any point on this line by starting at the given point, 1, 2, 3, and going in the direction of the vector 4, 5, 6 for some amount of time. So here we're thinking about t sort of like it's time. Like if we wanted to find out where we ended up 2 seconds after starting our travel from this point in this direction, we would just plug in t equals 2 and it would get us the point that's along this line 2 time units from this one. And maybe you've seen this notation, maybe not, but we use r of t, r with a vector hat on it, and then thinking of it as a function of t to describe this formula. In other words, we're thinking about these points not as just points, but we're thinking about them as outputs from this function r. So a better way for me to have labeled these points would have been to say that 1, 2, 3 is the point r of 0. The point over here, this would be r of 2, and the point over here was r of -1. I'll also note that we could combine this expression into a single parenthetical. In other words, if we combine all the x components, so 1 plus 4t, and then combine all the y components and all the z components, just using vector addition and scalar multiplication. And so if we write it like this, we can really see that this is a point, this is a location in space that is being described as a function of a time t. So another way to say that is to say that this is a point or a location described as a function of what I'm going to call a parameter. This variable t that's telling us different points along this line, that's a parameter. And so this in gray here is essentially what a parametrized curve is. It's a function that tells us a location that changes based on the value of a single parameter. We usually write t, but sometimes we use s. You can actually use any single variable for our parameter. And also, I'll note that the x, y, and z components for this line, well, okay, they're linear functions of t. That's sort of what makes sure that this describes a line. But we could actually write in here any function of t, like anything, and that would still describe a location in space as a function of t. The only difference now is that the path that this point traces as t increases would not necessarily be a line. But actually, that's kind of good. We're going to see that parametrized curves let us describe a large variety of different paths in 3 and 2-dimensional space. Okay, so here's the more general definition for you. So again, I call them parametrized curves. Sometimes you'll see people say parameterized curves with an extra e in there. And we also call them vector-valued functions sometime, and I'll try to explain why in a second. But all three of these words mean the same thing. They all refer to a function, which we usually write as r of t, whose input is just a number, it's a single variable t, and whose output is a point. So it's a location, either in R3 or in R2, that depends on a variable t. And as such, sometimes we'll refer to these functions x of t, y of t, and z of t, because if the location depends on t, then its x, y, and z coordinates also depend on t. And actually, going back to that line example from before, those component functions are right here. Right? This is x of t, y of t, and z of t. So this is usually how we'll write parametrized curves. You'll just specify a different function of t for each coordinate or each component of the point. I also want to point out that going back to this other term vector valued function, sometimes we'll think of a vector valued function as a function whose input is a number t and whose output is not necessarily a point, but a vector. By now, we've been kind of conflating the two anyways, so there's not a huge difference. But occasionally, you'll see folks write the output as a vector like this, x of t, y of t, z of t, inside vector brackets. Again, there's no gigantic notational difference between these two things. It's just whether or not we want to think about the output as a location or as a vector. And sometimes those are the same thing. Sometimes we want to think of them as separate things. It'll usually be clear from context whether we're thinking of the output as a location or as a vector. So hopefully it's not something that you'll have to worry about all that much. So next, I want to do an example where we come up with a parameterization of a specific curve. And the example I want to do is kind of this initial parameterization that we'll be able to modify and use for a lot of different contexts throughout our study of geometry here. So we're going to start by coming up with a parameterization of just the unit circle. The circle in the xy plane with radius 1 centered at the origin. And like I said before, parametrized curves can live in two-dimensional space or in three-dimensional space. This one's going to be in two-dimensional space, but you'll use it in the future to help understand some parametrizations in R3, so it's worth knowing. So here's a picture of the curve we're going to be parametrizing. And so our goal is to come up with a function r of t that has two components, x of t and y of t, in such a way that as t increases, we are moving around this circle. Now, it turns out that the way I've written this prompt for the example, it's sort of underspecified in the sense that I haven't said anything about like where the parameterization should start. Like when t equals 0, where do you want to start thinking about the thing moving from? I also haven't said anything about how fast it should go around the circle or in which direction. And I'll touch on this again in a second, but all of that is to say that a single one-dimensional object, a single curve in either R2 or R3, has lots of different parametrizations. So let's nail down some details about this one. So we're going to parameterize this circle in such a way that our parametrization will start at the point 1, 0 right here, and it will go counterclockwise this way, in such a way that it'll go around the circle at 1 radian per second. So, okay, we're going to think about t as having units of seconds. What that means is that at t equals 0, we'll be here, and by the time 2 pi seconds have gone by, we'll have gone all the way around the circle because the whole circle has 2 pi radians. That also means, for instance, that by the time t is equal to pi over 2, we'll end up at the top of the circle because pi over 2 radians takes us from here to here. Similarly, this would be t equals pi and t equals 3 pi over 2. Now, I've chosen this specific parameterization because it is the one that most carefully matches our understanding of the unit circle. And what I mean by that is if we have a point on this unit circle here, then we can find the coordinates of this point if we know the angle that this point makes if we draw a line to the origin. And I've set this up so that if we're moving at exactly 1 radian per second, this angle here is always t. Usually we label it as theta, but the idea is we're kind of moving along this thing at the same rate as theta would increase. So bringing in a little bit of our unit circle knowledge, it means that the coordinates of this point is cosine of t sine t, which again, we could always figure out by kind of drawing a little right triangle here and using the sine and cosine functions, making note of the fact that this line segment has length 1. But actually, once we've made this observation, we're done because we've noted that the location of this point as it moves along the circle is given as a function of the parameter t by cosine t sine t. So that'll be our r of t in this case. So in summary, if we want to parametrize a circle of radius 1 in such a way that it starts at the point 1, 0 and goes counterclockwise at 1 radian per second, this is how we do it. Now, like I said before, there is more than one way to parametrize a single curve. So you could think about like how would we parametrize this same circle if we changed any of these conditions? For instance, if we started at a different point and we moved clockwise instead of counterclockwise, or if we went at a different speed. Let's talk about just one of those. Let's say we went instead of 1 radian per second, we're going instead at 2 radians per second. It means that we're going in the same direction around the same circle, but we're going twice as fast. So for this parameterization, I'm just going to call it r sub 1 of t just to give it a different name from the one from before. And to come up with this parameterization, There's a few ways to do it. We could annotate our picture here and say that after t seconds, this green parameterization that was going at 1 radian per second is here, but the one that's going twice as fast will be roughly here, and we'll make an angle not of t radians, but of 2t radians, because it's going twice as fast. Using that same unit circle knowledge means that this point will be cosine of 2t, comma sine of 2t. And so that's what should go here for this parametrization. Another way to think about it is that our parameter for this one should just increase twice as fast as it did here. So instead of writing t, we could just write 2t instead. That's an idea that we probably won't explore too much in our course, but it's called a reparametrization, where this parametrization traverses the same path, the same curve as this one, but goes twice as fast. So it goes along the same one-dimensional path at a different rate. Now, you'll get a lot of practice with coming up with your own parametrizations and connecting curves with possible parametrizations from them as you're practicing and doing homework with this. So leaving that aside for now, the last thing I want to talk about for this lesson is what it means to compute the derivative of a parametrized curve. So if we have r of t and we know its component functions, like x of t, y of t, z of t, I'll note that all of this works just the same for parametrized curves in R2, so ones for which we only have x and y. The way that we take the derivative is just component-wise. So we're going to write it like this, r prime of t, and we're just going to take the derivative of each of these things and bundle them together. So we'll have x prime of t, y prime of t, and z prime of t. And if this was a two-dimensional situation, you just wouldn't have the z prime of t. So just for a quick example, if we had that parametrization from before, which I called r1 of t, but I'm going to just call it r of t, that was cosine of 2t, comma sine of 2t. So bringing that back, this parametrization of the circle of radius 1, if we take its derivative, then we're just going to differentiate each term on its own. So we have negative 2 sine of 2t, taking the derivative of cosine of 2t. And then for the second one, we have 2 cosine 2t. So, okay, it really is just that simple, but what we want to think about is, what's the point? Why would we ever do this? And the reason is, this has a very convenient and meaningful geometric interpretation when we're talking about parametrized curves. And to really see what that interpretation is, we kind of need to look at the limit definition of the derivative, which looks like the same thing it looked like when you were learning about single variable calculus. You take a limit of the value of the function evaluated at t plus h and subtract its value at t, and then you divide by h. Now, don't worry, you're not going to actually have to evaluate any limits or anything like that, but I'm writing this down because it'll help us understand what this really is. Let's bring back that picture from before of the circle of radius 1. So let's try to unpack this formula a little bit to figure out how to visualize it, like what this derivative should really be interpreted as. We have on top r of t plus h minus r of t. Remember that we're taking a limit as h goes to 0, so it makes sense to think of h as a small number. So let's say that r of t put us here. So t is just some number, and r of t is right here. It's this point on the circle. And let's say that h is just a small positive number, and so r of t plus h it's along the same path, but a little bit further in the direction that we're traveling. Now we're taking these two values, these 2 points, and we're subtracting them. What does that mean? Well, think back to vectors. Whenever we wanted to find the vector that pointed from one point to another, we subtracted the point at the tip minus the point at the tail of that vector. So the way to visualize this difference in the numerator here is just as the vector that points from r of t to r of t plus h. So that's what's in green here, but that's not the whole thing, because what we're doing then is we're dividing by h. And remember, h is a small number. Maybe just for our purposes, it's 1/3. So we're dividing this vector by 1/3. And since we're dividing by 1/3, that's the same as we're multiplying by 3. So this entire fraction should be represented by the vector that points parallel to this one, but is 3 times longer. So I've scaled this original vector to be 3 times longer, and now this green thing is r of t plus h minus r of t over h. So first of all, this whole thing is a vector. That's why I wrote this in vector brackets. It wasn't a mistake. The thing that we get when we take the derivative of a parametrized curve, whether you're writing the parametrized curve as a point or as a vector, the derivative is always a vector because it's found by taking the difference here and then scaling it. Now, this isn't what the derivative is because we still haven't thought about what it means to take this limit. Well, h is going to go to 0, meaning t plus h is going to approach t. So it's like we're taking the blue point at r of t plus h and we're sliding it towards r of t. We're thinking about what's going to happen to this green vector as we do that. But actually, let's jump into GeoGebra so I can show you an animated picture of what's happening as this r of t plus h point is approaching r of t. So over in GeoGebra, I've tried to recreate that same picture. We have that circle of radius 1. The point on it that's moving around it is r of t. R of t plus h is just another point on the same circle a little bit further along the path. That vector that was the difference of these two things looks like this. That's r of t plus h minus r of t. But when we divide by h, remember it means we scale this and we make it longer because we're dividing by a small number. So it looks like this vector here. And now the question is, as h goes to 0, so as this point goes to this one, what's going to happen? And maybe you can kind of already guess what's going to happen in your head because this is sort of looking like a secant line. And remember back from single variable calculus, we take limits of slopes of secant lines to get the slope of the tangent line. But as h goes to 0, this point gets closer and closer to r of t. And notice that even though it's getting closer and closer, this vector is staying roughly the same length, independent of h. That vector, the green vector, is about the same size. The reason for that is that r of t plus h is getting closer to r of t, so the numerator is getting smaller at sort of the same rate as the denominator, which is h, is getting smaller. So those two changes sort of cancel each other out. And in the limit, as h goes to 0, those 2 points kind of hit each other. And what's going on with this vector? It is tangent to the curve. So here's the actual tangent vector. This pink vector is tangent to the curve at this point, and this is what we get when we take the limit of that thing. So this is the derivative as a vector. It always points tangent to the curve in the direction that you're traversing it. So as t increases, as this point moves around the circle, so as t increases and this blue point moves around this circle, we're always thinking of the derivative, this pink vector, as the vector that is starting at the point r of t and is pointing tangent to the circle. So back in our picture from before, I've annotated it with the tangent vector. So this vector written in orange here is the vector showing up in pink here. And again, we always think of it as the vector that is tangent to the curve at the point r of t. Now, maybe it's not surprising that the derivative of something that was describing a curve ends up being something that's tangent to that curve. But the point of this whole discussion with the limit thing was to show you how that actually plays out and how to connect this formula and the definition of the derivative to the picture. And you'll see as we go forward, this will be very useful as we're dealing with parametrized curves. All right, that's going to do it for this lesson. You'll see as we go forward that parametrized curves really let us kind of actually do calculus on one-dimensional objects, either in two-dimensional space or three-dimensional space. They're super useful, but before we get into using them for those calculus applications, we're going to want to spend some time practicing visualizing parametrized curves and even coming up with them on our own. So happy practicing, thanks for playing along, and I'll see you in the next lesson.